I can start, cool. Early 20 seconds, all right. Hi folks, welcome to DAT304. My name's Tim. So who here knows, other than reInvent, what they're going to be doing at work every day, right? Every day's the same, it's really boring, everything happens exactly how it's supposed to happen. There's no natural disasters, there's no customer escalations, no maintenance windows and all that kind of stuff. Anybody? Hands up. You can't see, I can see there's nobody who said that, which is good, otherwise I think I might call you a liar. It never happens that way, it's a myth, right? And so it's best to be prepared for that kind of thing. You have to build a resilient system. We're going to talk today about some design patterns that we can use in Aurora for high availability and disaster recovery to build resilience into your database-based systems. My name's Tim Stokes. Shortly I'll be joined by Grant McAllister. We're both senior principal technologists at AWS, and we work on Aurora. So let's get started. My clicker doesn't work. All right, now it works. Cool. All right, we've got that one out of the way. So first, let's define precisely what we mean by resilience so we can know we're talking about the same thing, and if you leave the room, then we'll know why you left. So resilience is the ability of a workload to recover from infrastructure changes, service disruptions, dynamically acquire new resources or release them in response to demand, and to mitigate disruptions such as misconfiguration or transient network issues, things like that. That's what it means to be resilient. This is supported by two pillars: availability and disaster recovery. There's no one solution to any of this, right? There's a whole landscape of choices that you can make, these trade-offs between failure modes, performance, cost, and complexity of how we run it. So these trade-offs, I can't make them for you. They're made by you, the customer, with the tools that we can give you from Aurora and the rest of AWS. So we'll discuss today some of these patterns that exist at various points along the space and how you might choose to use if they're appropriate for you. First, let's explore these pillars a little bit more. So firstly, availability. Availability is the proportion of time that a workload is available to use. This is usually expressed as a historical measure over a period of time, like we might say 4 nines in a year, something like that, 4 nines in a month. Adding redundancy to a system is a really good way of adding availability to a system, and it avoids the impact of a single point of failure. That's availability. Next one's disaster recovery. We should also consider this in any resilience strategy. These are techniques and strategies used to recover your workload in the case of a disaster event. So this focuses on one-time recovery measures, right? Recovery objectives in response to natural disasters, large-scale technical failures, things like that. So here we use recovery time objective, RTO, to measure what we're doing here. The maximum acceptable time between a single impacting event and when we can resume service again, that's RTO. And then there's also the recovery point objective, RPO. That's the maximum amount of data that you can lose. Normally we measure it as an amount of time though, after a disaster or service outage, right? So we might say that we had some asynchronous network lag of 10 seconds, so the maximum thing that we could possibly lose is 10 seconds. That would be our RPO, right? So now we're speaking a common language, we can dive into some of these solutions, right? So since all of you sitting out there, I'm sure, have hundreds of different ways that you use Aurora, right? So you're going to have such different HA and DR needs. So we're going to explore this with an example, and hopefully you can see your face reflected in some of this example. Imagine that you're a DBA, right? Maybe that's not too hard. You've been hired as a DBA for this hot new startup, right? This startup runs a web store and it sells pictures of the sunrise. There's a joke there, if you can spot it, see me after, get a sticker. You have a small amount of angel investment funding because you're a startup, so you're choosing Aurora because you know it can start small with you and it can support this unicorn growth in selling pictures of the sky that we're going to get, right? So today we'll follow the journey of this startup as we go through its growth phases and see how it changes, how it thinks about its HA and DR needs. All right, so first step, the minimal configuration of Aurora. It gives your database durability across 3 availability zones and availability in 1. We call this a single AZ pattern. So there's one database instance in one availability zone, which balances your cost and performance. This instance is where your query processing is done, where your buffer pool lives, or your familiar database terminology happens there, right? So you can scale performance by increasing the size of that instance, or even using a serverless instance that does it for you automatically. There's no data stored there, though. This is where it's a bit different. This is where Aurora stores your data down the bottom there in this Aurora volume, in this big box that crosses all the 3 AZs. We call this Aurora storage. We'll talk more about it. This might not look super important for HA and DR, but it really is. It's the basis for a whole bunch of stuff that we do. So we're going to just drill into it a little bit more so that we can understand how these other features work. If that one database instance becomes unavailable for any reason, then your database becomes unavailable. But it's not a durability question at all. That storage is still down there holding the durability for your data. All right? So let's dive into this storage a little bit more. Aurora storage at the bottom, that green box, we're going to fill it in. That's a multi-tenant storage fleet spread across 3 availability zones in one AWS region. It's made up from a large number of special purpose storage nodes. Here I've just got 6 because I can't draw that well, but there's lots of them. These are responsible for storing your data. That's simple, okay. But they also carry out repairs. They also do heat management. They also offload a whole bunch of other stuff that Aurora is doing for you. It's all happening down there in that storage fleet. So here we can see those little small boxes. That means the storage nodes already contain some data from some other volumes already. Remember, it's a multi-tenant storage fleet. So because these availability zones are physically isolated, there's 3 of them, that means that barring any natural disaster, it's very unlikely that more than one of those availability zones becomes unavailable at any time, right? So Aurora first encrypts your data with your key, if you like, and writes it down to the storage nodes. It makes 6 copies of the data, spreads them out across the 3 AZs, but you only pay for 1 of those copies. For any new write, quorum of 4 of those copies has to be written to durable storage before Aurora says that the write is good, and we can move on to the next one. So this means that Aurora can handle 3 storage node outages. That's a whole availability zone plus 1 more before dealing with any durability issues, right? That's pretty impressive. You didn't have to do anything to do that. It comes out of the box. Okay, so what exactly is this data that we're storing here, right? This is where Aurora's a little bit different again. Aurora volume is divided into 10 gigabyte chunks. We call them protection groups or PGs. Storage features like repair and heat management, they work in these units of PGs. So traditional databases generally, they write a log of the things that they're going to be doing, and then they write the things that they're going to be doing. Well, Aurora just writes those logs. It doesn't write the pages at all. Right? And it writes them in a special Aurora log format to Aurora storage. Now the storage understands that format. So it understands how to turn those log records into database pages, and it does that in response to so if it needs to do space reclamation or it needs to read them back again into the engine. This job's pretty easy if you don't want to read your data back, but we need you to read your data back, right? So we need to apply those log records and read them back. So this is the secret to Aurora's performance because we're doing it in parallel across all those storage nodes, but it also underpins a bunch of HA and DR features which we're going to talk about. Okay, so Dawn Pictures, remember, we're selling Dawn Pictures. They're doing great. We're deploying the app, we're doing it frequently and smoothly. Database is growing, storing lots of those log records, until one day, your application developers, unfortunately, they release a bad build and you ship some black and white pictures or something like that, right? But don't worry about it because we have continuous incremental backup built into Aurora here, right? Each PG in Aurora storage is continuously writing those log records and database pages to S3, continuously. The storage is doing it, not the head node, not your database instance, so there's no impact on your performance here, right? We're doing it behind the scenes. Excuse me. You can set your backup retention to between 1 and 35 days. You can choose to restore at any point in time between that earliest restorable time you see at the beginning, that's set by you with your retention period, and your latest restore time. Your latest restore time is normally within about 5 minutes of now for any active database, right? So what you can do is you can choose the time using maybe some application logs that you've got, something like that, and then you can say, Aurora, please restore me a point at this LRT point, and then we'll restore it back. We'll make a new volume, we'll make a new instance, you can check it over, you can run your application against it, you can decide whether you picked the right time point, things like that. We're not changing your original instance or volume while we do this, okay? Once you're satisfied, you can bring it back online as your primary database if that's what you want to do. Okay. But what are we doing when we're doing a restore? We'll drill into this a little bit more. So remember, we stored all those older database pages and log records to S3. It's all been saved in there, and so what you're going to do is you're going to tell me the restore point. You're going to use point-in-time restore, PITR, in order to do this through the RDS console, for example. It's a console screenshot down the bottom, so that's telling you when the LRT point is. You can find a point in there, right? So here we can decide that ×7 is the one that we want. That's what you've decided to tell me, okay? So then what we're going to do is we're going to restore the latest copy of all of the pages before that point, right? And this is going to happen in parallel across all of those storage nodes that we saw before, right? And then we're going to take all the log records that came after that point, up until ×7 in this case, and we're going to apply them to the page. We're going to redo those instructions. At that point, those database pages are at a crash-consistent point from the database engine's point of view. Then the database engine takes over and does its normal recovery, which is only really fast because it's only talking about a few seconds of time normally there rather than many hours perhaps between your last checkpoint for a normal database engine, okay? So it's a bit different for MySQL and Postgres, the way that it does that last little step, but all the Aurora things underneath are the same. Okay, so like any good DBA, you learn from this event, right? And you went and had to talk to your developers and you said, hey, we need to do something a bit different here. We need a different way of doing testing. Now, we can't test in production. Obviously, we've tried that, didn't work too well. We can't test, but we want to test on production-like data and with production-like workload and performance and everything else. Otherwise, we can't do good testing. So what we're going to do here, rather than just duplicate everything, which takes a lot of effort, takes a lot of money, is to use Aurora clones. So here we've got the setup. We've got our production instance and our production storage in our volume with some log records and pages. Then we're going to make a new clone down the bottom there. You can see it looks a little bit different. It's kind of hollowed out, is what I'm trying to show you, right? There's no actual log records and pages at the bottom there. There is a new instance. There's just a whole bunch of pointers up to the volume. So now when we read from the volume, the clone volume, we just follow that redirected pointer and read from the original thing if we haven't changed it yet. Storage is doing this for you. There's no separate indirection or anything there, so there's no change in your performance. Right? When we want to write to a log record, we break that little indirection and we write your new copy inside the clone volume. Right? And then we can read it back again directly, no problem. If we wanted to write to the original volume, same thing happens, just in reverse. First, we copy out the old copy into the clone volume so that you can keep that copy for your clone, and we break the indirection pointer and we write your new data into the production storage there. If we expanded one or the other volumes, that's completely fine. We can just write to new space inside each of those volumes, right? So what's happening here is you're only paying for the changes in the data. So here we've only got a few boxes down the bottom that have been filled in. So you're only paying for the storage size of those few boxes and the second cloned instance that you're using, which can be a different size too. That's up to you, right? That's the magic of clones. So in the Dawn Pictures startup, right, your CTO, he hears a quote from Werner Vogels, the CTO at Amazon, that really resonates with him. You might have seen it on a T-shirt or something. It says, everything fails all the time. And this is true. So you can talk to, use the CTO, you talk to your CTO and say, I'm happy with this 3AZ durability story that we've been talking about, right? But I think we need to lift our game on our availability story. Aurora gives us an SLA of 4 nines if we're doing this inside one region, and we want to try and hit that. So that's about 52 minutes of downtime a year if you do your maths. So let's see how we can do that. To do this, we have to engage more than one availability zone. Here we've got 2. So what we've done is we've just created a second instance in separate AZ in this case, because we're trying to do it for availability. And the same Aurora volume. We're not duplicating any data. We're not synchronizing any data. All the data is still in the same Aurora storage place. We bring up that standby. You can see there I've got RHG 16XL, so both the same size. That's not required. But what we've done here is we've chosen to do it this way, such that when the primary has a failover event, standby can take the same amount of load because it's the same size, right? Okay. So there's no discussion here about RPO, that recovery point objective. This is what we'd call RPO 0 because it's just one piece of shared storage. Okay? Whilst this is happening, or before the failover, the primary is keeping the standby up to date with any new transactions. All right? Normally that failover takes between about 30 seconds, okay? So we can deal with that. We're back to operation again. So as we grow a bit more, then you might need some more read transaction throughput too. So you're already using a pretty big instance there. It's not the maximum RHE. You could go a bit bigger, but we say, I need some additional read throughput. So what we can do is that second instance that we already added as a failover target before is also a replica without you doing anything else, right? It's also a replica. It's also able to handle read-only queries if you only ask it, okay? Like I said, the writer is keeping the replica up to date with any new transactions within a few milliseconds normally, so there's a little bit of lag that you'll have to deal with if you're trying to do read-only transactions there. But otherwise, it's completely hands-off for you. So what's happening is we point our application at the replica and you ask it to do read-only queries. So here you can see that's 70%. That's me trying to say that they're both running at about 70% load of the maximum load that they can do, all right? So that's a bit of a problem though, because when the primary fails, if we imagine that the load stays constant, you've now got 140% of an instance being used. Now an RHE is pretty good, but it can't go above 100%, right? So we've got a bit of an overload problem here. So the read replicas helped, but they've left us with a different problem, all right? So how can we deal with this? What we can do is we can just keep on stamping out this pattern. We can keep on adding replicas. Here I've got 3, but you can do some more here. You can make them different sizes. And if we just pay attention to that number there, 70%, 70%, and then if we have a failover, then now we don't go above 100%, right? So we're not having that overload problem. Okay, so because we've chosen in this case to put them in 3 availability zones, we could actually make availability zone 1 and 2 unavailable, and we'd still have some service. AZ3 would still be up. We'd be back to the overload problem, so we'd have reduced performance, but we'd still be up, okay? So as your load continues to grow, right, even this is maybe not good enough. You maybe need some more performance headroom, okay? So you can continue to add up to 15 of these replicas in a region. They can be different sizes. They could be serverless even, where the sizing happens automatically for you, right? If we see, I've got the original couple of 16 XLs there, and then I've made some smaller ones as well, and 8 XLs. So that's good for read replica traffic, but like we said before, we don't really want to fail over to those smaller ones, right? So what we do is we tell Aurora through this idea of a failover tier, said this is the order in which I want you to choose instances when you fail over. So things in tier 0, the lower number, are going to be chosen more readily than things with higher numbers, okay? And if there's any choice in between, it'll choose the one which just has the size of the outgoing writer. We'll try and match the size as well, so we don't have that overload problem, okay? All right, now we've added all these replicas, that's great. But your application needs to be able to talk to them. It needs to know which ones to talk to at that time. If you're doing writes, we need to send the writes to the writer. But the application has to even know which one is the writer, because it changes when failover happens, right? So here, Aurora gives you the concept of endpoints. We've got the writer endpoint, or the cluster endpoint, and we have a reader. The writer endpoint obviously points to the one that's the writer at that point in time through the DNS, and the reader points to the set of, using round-robin DNS, all the ones that can accept reads. All right, so rather than hard code this in your application, the IP addresses use the DNS names, and DNS will deal with it for you. So this increases your availability, right? By reducing the time it takes your application to discover this new topology change when a failover happens, or when a replica is added, or something like that, when autoscaling kicks in. Okay? You could even configure a custom endpoint for yourself to maybe arbitrarily group some endpoints together. Maybe we'll say these are the ones that I want to handle my front-end traffic, and these ones handle my back-end traffic, something like that. All right. Cool. So we've got all of these. The fleet is growing like crazy, right? You've got this front-end application fleet, and it's a pool of EC2 instances, and it's running PHP. No judgment. Another pool of stuff's running Java on the back end, right? So each of these servers is making connections into your Aurora endpoints. Here we'll just talk about the writer side. It happens the same thing on the reader side. It just makes the slide too busy. So this brings resilience challenges too, because all those connections, they use horsepower, right? They have a socket slot. They reconnect all the time. They have to authenticate and authorize. They do TLS. They do all those kind of things. And even when they're idle, they consume resources too, I'm sure you're aware. So we want to try and get control of that connection management, right? So what we can do is we can limit and we can pool. There are the two techniques that we have in our toolbox, right? By limiting connections, you avoid the oversubscription problem, but you might limit your performance too. And by pooling, you can start to restore some of that performance back again by reusing connections, right? So many driver packages like JDBC for JVM, if you use that, they already deal with some level of pooling for you. But one of the challenges is it's not aware of what's going on in a clustered system behind the scenes like what Aurora has. It's only aware of single node databases. So we'll talk about how we can deal with that. So if you were to try and deal with this yourself, on the end of each of those connections, you'd have to have specific logic which talks about, hey, when the failover happens, I'll get an error back from my writer. Now I need to recognize this specific error and I'll need to do some specific action like reconnect properly and redo my transactions, things like that. And you also have to deal with the fact this is not instantaneous, right? DNS normally takes 30 seconds or so to flow things around the world, depending what your setup is. So we're going to have to deal with this. What we do is we give you this AWS Advanced JDBC wrapper driver. It's aware of what's going on inside the database cluster topology, right? It knows that those nodes are there. It knows their jobs. And it knows when this changes. It knows this much faster than the DNS tells us. This is not using some AWS secret. This is an open source thing. You can get to it if you like. And what it's able to do is it's able to handle this failover within up to 66% faster, right? So that's within about 6 seconds, maybe even quicker, depending how you configure this plugin. We've recently announced, there's a GitHub link there if you want the QR code. I'll put that up there so you can take a picture. But we've recently announced a new Failover 2 plugin in here as well, which makes this even faster. So I encourage you to have a look at that. If you've been using this before, it's different, it's quicker. And also, it's not just about JDBC. Everything I've said here also works for Python, works for Node.js, and we have a MySQL ODBC driver there as well. Camera's down. Okay, cool. Next one we can do is RDS proxy. This gives us a bit more control over what's happening in a more stateless fleet, like the PHP thing we had at the front there, remember? We don't have a lot of state to put connection management things into. So with just a few clicks, you can set up RDS proxy in there in the console. You don't have to go and configure anything, just say turn proxy on. You just have to configure your application to go and talk to the proxy endpoint instead of that reader and writer endpoint that we had already, the cluster endpoints. Proxy still gives you the idea of the reader and writer endpoints just at its level. So with proxy, you don't have this complex configuration anymore, right? We just take it all out into a proxy layer and we have these pooled connections coming out the back of the proxy. So now we'll just focus on the reader's side. We used writer last time, okay? So our application's making many connections in the front. We've got some different colors to show us what's going on. And we can see that the yellow session's running at the minute through this one back-end pool connection. Of course, you'd normally have more than one, but my drawing's not that good. So yellow one goes through, no problem. Okay, now your blue one's gone through. It had to wait, it was queued up because we had a maximum limit of 1. So the blue one's executing, and then the blue one's done something, in this case, a prepared statement, that's caused pinning. So pinning means that this pooled connection in the back there can't be used by some other statement that comes after it, some other session that comes after it. It's mutated its internal state. Maybe it's done some locking functions, maybe it's called a prepared statement, called a stored procedure, a few other things. It's made it pinned. If you're worried about what's going on with pinning or you're looking for some visibility, we can see that CloudWatch metric up the top there that tells us how much is going on. It's in your best interest to avoid pinning as much as you can by telling your application to avoid doing these things too much, okay? So what happens when failover happens is that the front-end application, the connections will not hang up. They won't even notice that the failover has happened if the session was not pinned. So here we can see the purple one's now executing. The yellow one did not see a disconnect. The purple one did not see a disconnect. The blue one did because it was pinned. It did something with pinning. okay? All right. So, business is great, selling Dawn pictures. Who knew, right? Your startup has raised some big amount of investment, and it's time to go global. So for the DBA, this is a little bit challenging, and remembering what Werner said before, everything fails all the time. You decide that your data's got to be durable across even the unlikely event of a full AWS regional outage. So now I'll let Grant tell you about that. This is Grant McAllister, who'll talk about global resilience. Thanks. Oh, I've got a clap. Good work.
Thank you, Tim. So, as your business grows and it expands, one of the things you have to think about is global resilience. Our regions are very durable and very highly available, but I don't know how many people remember Sandy when it was coming to hit the East Coast. There was a lot of people very worried about the US East 1 data center. Now, as it turns out, it was just fine, but those are the kind of events that could be worse, and you really want to think about, protecting your business. So as our business has gotten bigger, our leadership says we need to think about this. So the first method that we consider is cross-region backups. So I'm showing the same sort of setup that Tim had in region A, our primary region, and we'd really like to have some protection in region B. So the easiest way to do this is we can take a backup of our database by just running the create db cluster snapshot command, and that's going to store it in S3 as part of the service. Then what we can do is we can do a snapshot copy with the copy db cluster snapshot command. Now it's in the second region. So the interesting thing about this is actually asynchronous replication when you think about it, right? Now, it's kind of weird asynchronous replication because if you're doing it every hour, for example, that's the lag, right? That once an hour you do this. Now you could choose a different timing. You could do it every 10 minutes. You could do it every day, but you can choose. Now, got that backup done, great. Let's say one of the picture sales comes in. We got that in region A. Oh, region A has a problem. Well, that's the challenge, right? The backup was taken without that picture, we don't have it. So our RPO, basically the amount of data that we could lose with this kind of solution, is somewhere probably in the 10 to 70 minute range. And the reason why I give you that is, let's say the snapshot takes 10 minutes, and if you're super lucky, you've just taken the snapshot right before you have the problem. If you're unlucky, like I usually am, the snapshot happened, 59 minutes ago plus the copy time, which means I've lost more than an hour's worth of data. And that's bad, and that's why I've kind of labeled that as sort of yellow. Like this works, but if you're doing hourly, there's definitely a lot of RPO. But the good news is we do actually have a copy of our database in the second region, so we haven't lost all of our data. So now what we can do is we can restore that DB cluster, and then we can create DB instances. So this all works. You're back up and running, minus a little bit of data. So the RTO is going to be around, let's say, 60 minutes for this, because you've got to do a restore, you've got to create your instances, you've got to get your apps back and running. So again, in yellow because this works, and maybe it's fine for the business as it starts, but as we grow, maybe not. So there's another kind of failure I want to talk about, because as Tim was saying, things do fail. And the classic failure we think of is the whole region going down, but that's actually not the worst thing that can happen. The worst thing that can happen is a network partition. So what do I mean by that? What I mean is that from your perspective, outside of the region, like where you're living, you try to get to that region, you can't see it. Region B can't see region A. But everything inside region A is still going along, right? So the process that ships pictures out, guess what? It runs. It sends the copy of the picture to the, to your delivery service, that's went away. So it's not just that you missed the data of the sale of the picture in region A, you've also missed the shipment, right? Because that network partition time means that you're also unavailable. So this is just something we'll explore as we go through this. Now, this all looks super complicated, but we have a nice service called AWS Backup that integrates with Aurora and simplifies this whole kind of orchestration and makes this much easier. So the next step in our sort of journey as a business is to really think about reducing both our RPO and our RTO. And what we're going to look at is our global database offering from Aurora. So we start with a storage-only offering. And what that means is in our region, we're going to have another region, region B, that we're going to do work in. So the create global cluster command, you can either run this before you create any clusters, or you can add an existing cluster to it by doing create global cluster and referencing the original region's cluster. And then you just do a create DB cluster in the second region, and now you're going to have storage in that region. And this is one of the special things about Aurora is it's storage-based replication. So we don't need instances in the second region. What we do behind the scenes is we set up a replication server and agent, and then we start replicating from the current system to that server, then over to the agent, and then into the storage. And again, this is asynchronous, but the difference is the replication lag is usually in milliseconds, not seconds, minutes, or hours. So when your picture comes in, boom, it's going to be in both regions within a couple milliseconds, right? When I say a couple milliseconds, I mean probably a couple hundred milliseconds, depending on your regions. So the RPO is definitely typically sub 1 second, and again, still plus the network partition time. Another really nice thing about global databases, you can do local backups in each region. So you can be protected in not just the running system, but if something else happens, like someone drops a table, you can have independent copies there. So region A now having an issue, so that's not good, but we can easily fire up database instances in the second region, and then we can do a failover global cluster. Now this is important, the -- allow data loss, right? This is because this is asynchronous replication. And region A and region B are not necessarily going to be in sync. There'll be a couple milliseconds of difference. So you have to know that you're actually going to possibly have a divergence here. But once you do that, we have a read-write node. You can fire up your applications, and you're running again. So this means your RTO is around 15 minutes, maybe a little less, depends on your scripting. And the reason is because you had to start those instances, you had to start your applications. It's not really all set up, but it's pretty good, right? So, that's nice. The thing you have to think about when doing resilience is you have to pick where your destination is going to be. So we have a lot of different regions around the world, and here I'm showing my source being in West 2, i.e., Oregon, and then my destinations being AP Southeast 1 and the 2 US East regions. And we can see from the latency that we're kind of in the 170, sub 200 millisecond range to AP Southeast because it's a long ways from the west coast of the US, right? And we see spikes up to maybe 250 milliseconds. Not too bad. If we choose one of the US East regions, much closer, right? Just hopping across the US, sort of in the 60 to 70 millisecond range. And you'll notice that East 1 and East 2 are fairly similar because they're roughly located in the same regions. So now if you pick the 2 farthest regions that we have in the world, you're going to have obviously the highest latency. If you pick the ones that are closest, that's better. But of course, then how much resilience you're doing gets smaller, right? So that's a sort of trade-off that we have to make. Now, the next step up for our business is to go to a symmetrical configuration. So what do I mean by that? So we have our region A, and now for region B, what we're going to do is make an exact same copy. So we're going to run the same database instances over there. They're running in read-only mode, and we're going to start all the replication. So they're actually up to date, just like the local read-only nodes. And you can have your applications running as well there, and I'll talk a little more about that. So in the case of failover, or failure, now we can just do the failover command. We don't have to create the instances because they were there, right? So this improves our time quite a bit. So now we're talking about an RTO of less than 2 minutes. And we're working on speeding this up every year. So it's going to continue to get better as we do more optimizations. So let's talk about that network partition again. So if we have a network partition in this kind of setup, what you'll notice is at the moment we basically have 2 read-write nodes because we've done a failover, but we haven't been able to isolate that region yet. But as soon as that region is back unisolated, we will change that node to read-only. But that means there could be transactions taken during that time, and it's something you have to understand as part of this asynchronous workflow. Okay, so when we're done failing over and we're back running, we're not resilient, right? Because we only are in region B now. So what we have to do is get region A set back up again. So the first thing we're going to do as part of the service that we do automatically is we take a backup of the region A cluster. And the reason is because the region A cluster may have data, again, that wasn't replicated to region B. So we want to make sure that you can go and restore that and look through it, do some data diving to figure out if you do have differences. Once that's done, we're going to set up the replication server and agent going the opposite direction this time. And then we have to synchronize because, again, region A's data is different than region B. It's probably ahead of region B. Once we synchronize, then we're back replicating and you're back to your resilient setup, right? And this happens all automatically. You don't have to do anything. As soon as that region's back healthy, we do this. So switchover is another method to move from one region to another. Now this is a non-data loss one, typically used if you just want to move from region A to B. So in the case of like that Sandy, you might be like, this storm is forecasted. I want to move ahead of time. You can use switchover. It's also a good way to test your DR setup by switching and just making sure everything is how you think it is. So the command is switchover global cluster. Notice no data loss on the settings here. And what we're going to do is we're going to immediately make the read-write node read-only so that we stop taking any new transactions. Then we wait for the replication and we verify that all the data is in sync. So now these two regions are exactly the same. And then we promote region B. So and you can see that region A is read-only, region B is read-write. So we've now basically switched regions, but again, we're not resilient because we have to get region A back to being part of the global cluster. So we can just set up the replication agent and server and start replication because these regions matched. We don't have to do any synchronization. We've also improved our switchover time quite a bit. Again, that was one of the things that the team's been working on this year, which is really good. Now, one of the other things for resilience is making sure your application can actually figure out where to talk to the live database, right? So in this kind of global nature, each of the databases has a different endpoint. So this is the CNAME for region A's cluster, and that's vended by Route 53, our DNS service. And of course, region B has a different one. And you can actually see that the subdomain here is region A in one side, region B in the other. And that's, they can have different other names, but they're going to be different, right? So how do you know what to use? And before, we didn't have global endpoints. So you actually had to configure your application to switch this on failover or switchover. But now you can do a describe global cluster on your cluster, and what you'll see is this new endpoint there that I have in purple. And you can see that we really wanted to make sure that you knew it was global because we put global in the name twice. Not quite sure why we did that, but it's in a different domain, or subdomain, which is part of it, but we also, for our naming standards, we added it as well. So that's the key. Region A is currently our primary region, so if you ask for a resolution on that global name, it's going to point to region A's CNAME. So if we do a switchover or failover, again, what we're going to do is we're going to make this read-only, region A, and then we're going to promote region B. All good, right? And at that point, the resolution happens differently. What it's going to do is it's now going to resolve to the CNAME for region B. And the good thing about this system is we don't actually have to use the control plane for Route 53. We have these health reporters. This is all very highly available, so this is sort of guaranteed to work no matter what's going on. So this simplifies your resilience from a global perspective for your application, so it's much easier to get your application developers to make sure that their settings are correct when you need to do this. The other area that you can work on to really help resilience on your application and database is read resiliency. So I have the symmetrical configuration again, and in this case, what I'm going to do is I'm going to change part of my application to be able to function read-only. So this might be the listing for our pictures, right? It doesn't need to be able to write anything, so you just can show what's for sale. So now we have that now running across both regions. This will give you better latency because possibly you're closer to your customers. And now when a failure happens, those read-only nodes can keep running while we're doing a failover or switchover. So this allows you much better availability than you'd get if you were just running read-write because you don't have that couple of minutes while you're doing a switchover or failover. Now, if you do this setup, you can also do write forwarding. Now, because the challenge about doing a read-only application is sometimes there's some little bits of code that need to write something, and that's kind of painful to tear out of that application. So instead, what you can do is turn on write forwarding. Now, normally, if you didn't have this, you would have to have a VPN tunnel back to your application in region A. You'd have to send those write requests. It's a lot of complex stuff that's very fragile. Instead, what we're going to do is enable global write forwarding. This allows us to virtually look like we're able to write now to that cluster. And we're going to just forward the write back to region A. So we're not multi-writer. This is still a single writer system, right? So there's no magic here. It's just forwarding things backward, just simplifying the process. And then what we have to do is we have to wait for those things to get replicated back for us to see them. And that's kind of crucial, for your application to be able to read what you just got from a consistency basis. So let's talk a little bit more about the consistency. So we have a bunch of settings on this write forwarding feature that's important for resilience around session read visibility. So you can set that. I'm showing the APG one. There's also one for the MySQL. And the default is session level. And what session level means is read my own writes. So if I do an update, it's going to get forwarded over, and I have to wait for that to come back, and I get 195 milliseconds. So not bad. This is across pretty wide range, US East and US West. But my select has to wait for that propagation of my write to make it sure that I'm there, right? So that I can read my own write. So this is going to take 76 milliseconds. So it takes a while for that replication to go across the country. But the good news is I'm reading my writes, so I'm not going to have any problem with my application getting freaked out by seeing data that it shouldn't, right? The next select, because we haven't done any changes, only takes 1 millisecond, because we can read locally and we don't have to wait, because we are reading our writes because we haven't made any more changes. So this works pretty well, but you can see obviously that first select takes a bit of time. You have to be aware of that. Now, if you don't like that speed, you can go faster with eventual consistency, but that can be challenging as well. So our update, same thing, takes 195 milliseconds. Our select takes 1 millisecond. That's great, right? We're all happy. Performance. But my previous write's not visible. So, my application developers might be unhappy if I set this in the database. Now, the other option is global read visibility. And that's kind of as scary as it sounds. And I've marked it in red because you really have to be careful about this one. It does give you full global read consistency. So if you do your update, same thing, 195 milliseconds. Now I do a select, we have to wait for it to propagate, but if I did that select at t, what I have to wait for is all the things that were happening at time t on the primary, not just my write, but everything has to be propagated back across. So that takes 205 milliseconds. But all writes are visible, so that's really helpful from an application design perspective. But if I do any select, it's going to take 205 milliseconds because I'm waiting for the time that I have to wait for all the writes to become visible, right? So this is a nice feature if you want this visibility, but you can imagine from a resiliency perspective, you're kind of being held hostage by the replication lag. So this is very, you got to be careful if you're turning this on. Like I said, it's useful in a lot of cases, but the other thing we can do is we can run multi-region with global databases. So here I'm showing our region A and region B like we had to set up in a symmetrical configuration. But we can have up to 5 destination regions. So here, region C, what we see is that it's just a volume, so it's just storage only. So they don't have to be the same. You can make them different. So you can configure them to whatever level of cost and RTO that you want. Now, you could also make this symmetrical. So now we have 2 symmetrical destinations. And if you have something like this, we have an interesting offer on Aurora Postgres, which is around RPO. And we have this setting called Global DB RPO. And what this ensures is that at least one of your destinations will be within that RPO time, and it's in seconds. So if I set that to 20 seconds, what that means is that I won't take a commit on region A unless one of the regions is within 20 seconds of replication lag of region A. So let's walk through that. So I do my commit, 200 milliseconds to region B, 100 milliseconds to region C. So this is fine. We're inside of the RPO. We commit. Now region C gets to 60 seconds. It's having some kind of problem with the network. But we're still fine, right? Because region B is still taking commits because it's still doing 200 milliseconds. But we have network partition happen now. This is the scary one, right? So that happens, and region B is now at 21 seconds. So essentially it has tripped over the 20 seconds. And what will have happened is that at 20 seconds, those commits will start blocking. What this means is that you're free to fail over to region B and know that the maximum data loss is 20 seconds. Now this is configurable, you don't have to pick 20 seconds. But if you have financial transactions or contracts or things where you need to guarantee that you're not going to lose more data than X, this is actually a useful feature. It's not widely used, but it is one that like some of the financial folks use. So it is useful when you get really into those kind of scenarios. Now, another area that I like to talk about is cross-account, which is strictly not really global per se. It can apply to local, but I'm going to show a global database example. So when we have our two regions, everything is set up across one account, account A, right? So that's good unless something happens to account A, right? We won't want to talk about those kind of scary things, but it can happen. What we can do is we can set up an account B, and we can, with AWS backups, we can set up snapshots that are taken in each of the regions and then copied into our account region in account B. By this way, we're protected against anything happening in account A. Now again, this is asynchronous, so again, the same sort of, RPO is going to apply here, that the frequency of your snapshot is going to be the amount of data that you're going to be missing here. But again, a very powerful thing that's actually very easy to set up in AWS backups. So let's walk through our whole journey as a company. So we started off with just a single instance and a single availability zone. And then what we added was two multiple database instances in different AZs, so we had maximum available for multi-AZ. We added storage only, region B global database. We made that symmetrical so that we had lower RTO times. And then we added region B, and finally we did backups in all of those regions, right? And this leads us to a very good RTO and a very good RPO. And with that, I'm done. Here's some other related talks that are happening this week. Some may have already happened, but you can always catch the videos. And thank you very much.